Hello, hello, hello. Welcome back. It is Thursday, the 4th of December. We already have 5 people in the chat, and today is the final live stream before interviews start next week and the week after. I don't know about you guys, but I am feeling tired. You can feel it coming. You can feel it ramping up. From all across the board, the requests for mock interviews is coming, and everyone can kind of feel it, can't you? So I thought we'd go on today. Hello, hello. Thought we'd come on today. We'll do a little bit of last minute work, really simplifying and consolidating. I've got some questions I want to go through, including a little bit of the chemistry for the natural sciences people out there, stuff that I haven't gone through yet. Bit of graph sketching, and then sort of final thoughts, and speaking a lot about like the mentality behind an interview and the way to think, like prepare for it in the last seconds as you're about to enter the room, the mindset of it all. As always, do let me know what interviews you guys are going in for, because that might inform the order in which I do certain questions. I think I'm going to start today with some of the chemistry just to get that out the way, and then, no offense, and then get into some graph sketching, and then the final sort of physicsy question that I've been giving to all my mock interview students, that I think is really good to kind of give you a sense of the flavor of an interview. And I think I'm not going to do anything too crazy today. We're not going to be doing any like insane derivations, or really, really out there questions. As you get closer to the real thing, I think you really just want to be consolidating your core skills, taking it back to the syllabus, because whatever question they pose, no matter how weird it looks, can always be tackled with simple syllabus skills. And so if you trust those skills, you will be fine. Got someone in the chat saying, you've got a maths interview, but you like the way I structure questions, and the graph sketching is obviously useful. Well, okay, I've definitely got a cut, in which case I will do not one but 2 graph sketches, just to make sure you get something useful out of this. And when you say about the way I structure questions, actually, there's something to that, because that's definitely what I want to talk about today, is what that style is and what that communicates. Because I think the way to really impress in an interview is to show them that you have a reverence for that small detail, where it's not just like, oh, this and this and this and this. It's like, no, 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 hold on a minute. This, and therefore this, and therefore this, and therefore this, and every step matters, and here's why every step matters, because that shows you've got really strong, deep foundations on top of which they can build greatness. Some more chats. Can you do circular motion and simple harmonic motion? I find myself so confused in interview questions for these topics. Great news. Vertical circular motion is on my list. You got your maths interview at Queen's. Very worried about if it matters if I get it right or not. No. It helps to get there by the end. But again, this is more about your process than about the answers. They don't care about what you know. They care about what you understand. And the point of an interview is to push you past the point where you know what's happening, where you have to work out things. And there have been so many times in my comments where people have been like, did you mean this? And I went, yes, I did, because I've been making loads and loads and loads of mistakes. But the point is, even with those small mistakes, my ability has shone through in the way I apply myself to the problem. And so if you undergo that similar process in a math interview, even if you're making a mistake, they can point out that mistake and you can just correct it and learn something, because it's a lesson, not a test. Or you can be going through and thinking, does this make sense, on your own, and maybe spot your own issues and bring yourself back and correct it, which would be even more impressive. So no, it doesn't matter if you get it right or not. It's about the process. Another comment in. My engineering interview's on Tuesday, and I feel like I've lost motivation to do questions. Any tips? Well, that's very interesting, because I kind of lose my motivation to come up with questions. There comes a point where you kind of think, I've done everything, surely. And so what I would do at this point, that's why I can I would say stop going wild and out and just bring it back to core basics. Textbook. Go through the textbook, start to finish. Just think, what would be the interview question form of this? Do I like really understand this? Or is there anything lurking? Because what you should be doing at this stage, the big motivator here may not even be success. The emotional motivator here might be to avoid regret and think, what would it cause? What would have to happen for you to regret something in the interview? It might be coming out and thinking, gosh, damn it, I should have known that. I should have known that. That's in the book. That feeling is a feeling you don't want to feel. And that can be your driving force in these last few days. Bringing it back to basics, making sure you have no regrets. So if there's a really difficult problem you can't solve, you kind of go, okay, great, you win. But if there's something you should know, making sure you really show your best. How likely is graph sketching to come up? Rather likely. Can't guarantee it, but count on it. Like, especially if you're going for like a math or a science or an engineering, graph sketching is one of those foundational skills that like everyone has to prepare. Okay, so I'm gonna start with just a little bit of chemistry. So we're gonna basically just be doing syllabus plus today. A lot of this is stuff I probably should have done in last week's syllabus consolidation, but I was just holding the juicy good stuff for the final interviews, but now it's time to empty the tank. So first thing I'm gonna cover is mechanisms. Just reminding you that mechanisms are a good way of testing all of your underlying organic chemistry knowledge. So one that I've been asking is about Markovnikov's rule. So if we have, I'm just going to draw floating bonds, which will be assumed to be towards hydrogens. For instance, if we have an HBr molecule coming in, what's going to happen? Now, this is classic textbook, but you have to make sure every detail is correct and that you demonstrate why it's happening. So this is a polar bond. The bromine is more electronegative and pulls the electrons in that bond closer to it than to the hydrogen, leaving the hydrogen with a small delta positive charge and the bromine a small delta negative charge. This delta positive charge makes it an electrophile. It wants to move towards regions of electron density to pick up that extra electrons that it's sort of lacking. So this double bond breaks. Both electrons go here, and both electrons here go into the bromine to form one of two things. Either the hydrogen goes on here, leaving a carbocation here, or it can instead add to the second carbon, leaving the carbocation here. In both cases, then, the bromine minus with the lone pair and a negative charge then reacts to join that carbocation, forming bromopropane. And in this case, exactly the same thing is going to happen, lone pair going onto there, and that's going to form the same thing, but this time it's one bromopropane. And the reason this would be the major product, and the reason why would be because this carbocation is stabilized by the electron density in the neighboring R groups, which means that it is much more stable than this primary carbocation, so it's much more likely to form. And then they might say, okay, well, how about the situation where instead of it being propene, it is but2ene. I've used this in interview as well. And it might be tempting for you to say, oh, well, those would be equal mix of the bromine being there or there. But then the eagle-eyed among you will spot that in either case, it only forms a single product, because whether I form the bromine on the 2 or the 3, that flips around and it is the same molecule. So a sort of twist like that could be on the cards. Another really fun thing I've been doing is on physical chemistry. So I've been talking about the Haber process. Haber process, as those of you who need to know do know, is that we have nitrogen and hydrogen in dynamic equilibrium with ammonia. And the forward reaction is exothermic. I do A-level chemistry, but I'm applying for engineering at Cambridge. Do you think they could ask a chemistry question? I think it would be unlikely because it wouldn't really. Well, actually, I think I have someone who I'm doing an engineering interview with where they have been explicitly told that they will be asked chemistry questions. So it kind of depends. Like, it could come up, it may not come up. I would lean on it not coming up, but always be prepared just in case. Reason why I would say probably not is because I personally don't see how that prepares you very well for something like a mech-eng degree. I think that's for chemical engineering. Yeah, chem-eng, 100% chemistry is coming up all day, every day. But it depends. Do whatever it takes to, but again, no regrets. No regret strategy. I would personally think it's unlikely. You can see if anything has been given in the sort of the information you've been given from the college, or you could look up other engineering interviews. I would lean towards no, but maybe you want to be safe. Maybe you can think of parts of the chemistry syllabus that might relate to engineering, such as maybe corrosion and the sort of inorganic chemistry in that sense. So here, if we have this forward reaction being exothermic, you can get asked a question like, okay, what happens when I raise the temperature of the mixture? And from the Chatlier's principle, okay, well, I know that if the forward is exothermic, raising the temperature will favor the endothermic direction, so the dynamic equilibrium position moves to the left. And then I turn to them and I say, okay, I know it's because the Chatlier says so, but why? Can you prove it from first principles? And I kind of sit there and I'm like, oh, okay. So I kind of draw it out and I say, okay, let's say this is pure reactant. And let's say this is pure ammonia product. Let's say the equilibrium position was there. You're telling me it's going to move to a new spot. Why does it move? And then sometimes they'll come up with ideas. Sometimes they won't. If they don't, I give them a hint. Okay, let's consider rates of reaction. What are the factors affecting rate of reaction? And so they'll say, okay, as the temperature goes up, the molecules are moving faster, so they collide more frequently, and they have more energy, so a greater proportion of those collisions have sufficient energy to overcome the activation energy. So raising the temperature raises the rate of reaction. And sometimes they draw reaction profiles. So the forward reaction is exothermic and looks like that, where that's reactants, that's products. You have your activation energy. I'm just going to sketch this quickly. In the real thing, you should obviously do it a bit more fully. And the other thing I get people to consider is the Boltzmann distribution. Where the number of particles having a different energy. So it looks somewhat like this. And we know as we raise the temperature, the peak is lower and to the right. And we can consider the effect that has on two different activation energies. So we can say here, considering the amount of particles that had sufficient energy before versus how many have them after, it is a much bigger percentage increase than if the activation energy is lower. In other words, in both cases, a greater proportion have sufficient energy. But for the reaction with the higher activation energy, that percentage increase making it across the line is even bigger, which means that this endothermic reaction with a higher activation energy is increased by more. So then both rates of reaction increase, but the reverse reaction increases by more. So there's a net movement to the left. And then as some of that ammonia is being used up in that net reaction to the left, the amount of ammonia decreases, which means there are fewer particle collisions per second. So that rate of reaction goes down. And there are more nitrogen and hydrogen, so the rate of those collisions increases and that reaction rate goes up until they're equal again at a new equilibrium position. So if the rates were something like that, they both increased, but the reverse reaction by more. And then the one on the left grew and the one on the right shrunk until they were equal again at a new balanced equilibrium. And that was all I wanted to talk about when it comes to the chemistry. But things like that, thinking about not just saying because the Chatlier said so, all of this stuff is in your syllabus, and can you dig deeper and think why? Comment question. I have a physical NatSci interview at Cambridge, but I don't do A-level chemistry. Is it possible for me to be asked GCSE chemistry questions at the very least? Thank you so much. It's funny you should mention that. Someone left a comment on one of my videos that I responded to. Let me end the screen share. So one of my friends that I lived with in Cambridge for 3 of the years I was there, he was also Phys NatSci Cambridge, and he also didn't do A-level chemistry. I see Invisible Toast in the chat. Invisible Toast has started a YouTube channel, guys. He does really good math videos, and you should check him out. So I have a friend at Cambridge, and he was also Phys NatSci, and he also did not do A-level chemistry. And the reason why that worked for him is because he was doing math, physics, material science, and earth sciences as his chosen options. As he was applying, they knew he didn't do chemistry, but that was okay for him. Chemistry did come up in the interview. And you can go back and see like me talking about my interview experience, and you'll see that the chemistry interview was entirely based on graph sketching, which meant it was actually accessible to people who knew no chemistry. He gave the form of the formula, and my friend was still able to sketch it, and with some guidance from the interviewer, make sense of what it meant. The interviewer knows what you know and what you don't know. It wouldn't be a very meaningful thing for them to start poking you with things that you genuinely have no chance of answering. It doesn't give them useful information about your ability. Remember that an interview is a lesson, not a test. So they're just trying to find out where your limit is and push it. So if you walk out of an interview having learned something, it's gone well. So they will be responsible and pitch it at the right level. They can ask you some chemistry that they think maybe you will know, because there's chemistry comes up, for instance, in material science. So it may be worth brushing up on some of the fundamentals of the chemistry, just so you're not completely lost. But my expectation would be if they are asking you chemistry and they know you don't do chemistry, they would give you a bit more guidance. And it would be more of the out there process, or like my video that I did on learning on the spot. They can ask it to you, but their expectations about what you know should be managed and reasonable. So, in fact, I might even think that it would be quite good to use a chemistry topic to see what you do learning a new topic on the spot. Ooh, we have a maths interview for Cambridge on Monday. Well, sir, you have joined at just the right time, because having now finished my chemistry prelude, I'm going to do a little bit of graph sketching. And maybe do a little fun problem that I never really talk about, but it might be good for anyone who's doing pure. In fact, let's start with pure math, because I really like this one. You may have seen this before. Apologies if you have. But x to the x to the x to the x to the x to absolute infinity is equal to 2. Solve for x. There's an easy way to solve this, and there's a hard way to solve this. I'm going to show you what I would do first if I was in this position. I would look at this and think of logs. So I might say, taking ln of both sides, the power then comes out the front, and I get x to the x to the x to infinity. Ln x is equal to ln 2. Apologies if you do not like me saying ln. I am going to carry on. So this x to the x to infinity is still 2. So 2 ln x is equal to ln 2, which means that ln of x squared is equal to ln of 2. Oh my god! No, I didn't. Rookie mistake. Thank you for pointing out I am not currently sharing. We are professionals here. We're going to try this again, folks. Right, so x to the x to the x to infinity is equal to 2. Taking the natural logs of both sides is it makes sense to me whenever I see x in the power. So it's a tool I might reach for in my toolkit from my syllabus that would allow me to make some sense of this. So bringing the powers down, we would get x to the x to the x to infinity ln x equals ln 2. And then you can spot, well, that x to the x to infinity is 2. So 2 ln x equals ln 2. And ln of x squared is equal to ln of 2, which simply means that x squared is equal to 2. And so x is equal to root 2. That has to be the positive square root because shenanigans happen with the negative, which I will leave the pure mathematicians to ponder in a bit more detail. I will also add the easier path is to spot right away that this thing in the power is x to the x to the x to infinity, which is just 2. And you get there right away. So sometimes they do this sort of something to infinity where the idea is to just sort of replicate itself, either here to make that 2 or seeing it straight away to make that 2. It may be a skill you find useful in a math style interview. So that's on the pure math side. Now on the sort of general math, graph sketching that can be used for math or science or engineering. Oh, speaking of engineering, my engineering interview is tomorrow, and your vids have been super helpful. Do you have any tips for what to do on the day? Oh, stay tuned, sir, because I shall end with sort of my final advice for how to calm down and show your best work on the day. So that is coming. A couple of graphs I wanted to sketch. First graph, y equals sine x sine 3x. Ooh, I am literate. I can spell. Okay, so sine 3x. Well, what that's going to do? Yeah, let me consider that for a decent chunk of x. I know there are going to be zeros whenever sine x is equal to 0 or whenever sine of 3x is equal to 0. So I know sine x equals 0 whenever x is equal to n pi. And similarly here, sine of 3x is going to be equal to 0 whenever x is equal to n over 3 lots of pi. So every time sine 3x is 0, sine x is also 0. So I know I'm going to have zeros every n pi over 3, so they're evenly spaced. This. I'm also going to use the idea of an amplitude envelope. So I know that sine x varies between 1 and minus 1. Which means that if I multiply the whole thing by sine of 3x, this function in fact, no, I'll do it from the other way around. Sine of 3x is the one that varies. Let's consider that. So in this case, let's multiply by sine x everywhere. We will get something that looks like this. So in other words, the maximum it's going to be is the sine x curve, which if I do a sort of dotted line function for that looks like this. It will vary between sine x and minus sine x. Now, I also know, so you might expect to do something like this. I'm just going to do a sort of rough sketch at the moment, but then let's consider what's happening at these zeros. What's the behavior at these zeros? Those seem like special points to investigate more specifically. So what I might do is differentiate to find the behavior. How is y changing around that point? And if I differentiate, I'm going to get first, d second. I could do this in my head, but I'm not going to take any chances because I want to execute cleanly. Plus second, d first. So it's 3 sine x cos 3x plus cos x sine 3x. And I can see that at all of these 0 points where sine x is equal to 0, sine of 3x is also equal to 0, and so it should be flat. It should go flat in here. And then here, on the negative side, well, that's interesting. I'll get to that. Now, hold on. So here it's flat. So at pi over 6, it should be touching there. It should be at maximum, then the minimum, then the maximum, then the minimum. Let me ask a question. Where are we here? Because I just want to see what it does through that's what it does certainly within a little block. I want to find out what happens as I go through a block. Is it going to flip around and do anything weird? Well, let's look at what happens immediately as x is negative. I know that immediately, let me draw my component graphs just for reference, which I really should have done from the start, but whatever. And again, I'm just going to draw nice and simple, where this one's going to be minus pi and pi for sine x. Now, good form as well. Be diligent. I haven't been. You should be always labeling your axes, showing due care and diligence for the small detail. This one, sorry, of course, that's 2 pi minus 2 pi. And this first 0 would have been pi. So this first is pi over 3 and minus pi over 3. Let's consider what happens up to this first minimum. Sine x is negative. Sine of 3x is also negative, and negative times negative is positive. So I would expect it to come back around, go up, come down, go up. And I think that's going to do the same thing here. So here, after pi, immediately after pi, sine x is going to be positive. So yeah, it's going to do just kind of that situation. Like I haven't drawn this very well, but it should be sort of roughly, I imagine it like sort of in line. And I imagine those maximum points look like they all maybe want to be at the same height. So is this worth going into? Could you also consider odd and even functions? You absolutely could if odd and even functions are something you're fluent in. So both of these are odd functions, which multiplied together get you an even function. So it should be symmetrical about the y-axis. If you've got it, use it. Part of me is I just want to sort of. So I imagine that's what it's doing, but I do just for my own curiosity, just for completeness, I want to find other places where the derivative is 0, so I can find out these maximum and minimum points just to see if they are at the same y level. Oh, I wonder if I can do that a little quicker. No, not necessarily. No, I should. Okay, let's do this completely. Let's just sort of see if I can. So if that is equal to 0, first of all, I know it's going to do a whole bunch of. I don't think I want to get into the double angle formula of it all. Maybe not. Maybe I'll leave that as an exercise for the viewer. Just because I want today to be a little bit easier. And you can tell I haven't pre-planned these. I like these to be live solves so I can really put myself in the same position as you guys. Certainly got the general situation. It kind of feels like they want to all be the same height. Maybe because of a line of symmetry. I think yes. I wonder if I can exploit lines of symmetry. So these mirror lines. So at pi over 2, both sine x and sine 3x have mirror lines in them. And I'm going to make the argument oh no, is that so that's 2 pi over 3. And the average of those would be 1 pi. Yeah, the average of those, so that would be pi over 2. So pi over 2 is a mirror line in both. So I think there should be symmetry along all these mirror lines, which means it is just the same thing reflected time after time after time. That's fascinating. I haven't used that argument before. And so you get this kind of M shape, this sort of rolling N shape. That's cool. I like that. Again, I think this could be done analytically if I spent a lot of time really grinding through and finding like every single point where the derivative is 0 and then plugging them in and showing that these positives all have the same value, these negatives all have the same value. And by the way, I think that negative value is going to be -1. Because if I put in, for instance, sine of pi over 2, pi over 2 into both of those, sine of pi over 2 is 1, sine of 3 pi over 2 is -1, so it is -1. So I think all of these are -1. I think it's not as easy to see where the turning point on the maximum is, because again, I'd have to solve this. And I think these ones in between are going to be a little bit weirder because it's not going to be exactly on pi over 6. It's going to be a little bit to the right of that. So I'm not going to spend too much time on that. I think they might pull you away from that in the real thing, but there we go. That is how I've analyzed that. That's sufficient for me. Pure math knows maybe they would want you to really find those top lines, but scientists, I'm satisfied about that sort of weird sort of sound waveform. And the next one I want to move on to is y equals 1 minus e to the minus x for positive x. So we can say when x equals 0, e to the minus 0. Got a question before I launch into this. So in an interview, if you didn't spot the mirror value, how would you know that all the mins and maxes are the same height? First of all, you may not know definitively, but having an intuition for math and science is a helpful thing, even if you can't fully back it up. So let me put it this way. Saying nothing is the worst thing you could do. Having a gut intuition is better. Being able to prove it is the best of all. But you should always do the best you can do in any situation. So here, you could tell I was like, it really feels like it wants to be. And then maybe you could go about saying, if that were the case, and then maybe do a sort of try and knock that down, like a proof by counterexample or proof by contradiction. So like, okay, what if it were to be true, then all of these would be at pi over 2 and 3 pi over 2, etc. Plug those in. Great. Those are all minimum points, and they are all at -1. So at least these are the same. And from that point, you might get closer to arguing that symmetry anyway, because these are all the same. The zeros and then the ones, there's the sense of a periodicity to it, which implies that these should be periodic as well. I will also say that the symmetry, though, is used if you, instead of using cast diagrams, for people who use the graphs to get there. So for instance, we know this idea of the symmetry comes about because sine of 180 minus x is equal to sine of x, which means they are equal when sine is 90, which is pi over 2. You get these mirror lines. So maybe it's something you can play with, maybe not. But I would say basically do your best. Lay down your best, and they'll go, nice, that's where their best is. Let's push it further. And they might teach you a new skill on the spot to advance that just that little bit further. But everything I did, I was able to do with A-level syllabus material and a bit of intuition. So hopefully that gives you hope that even these more complicated ones, it may not be that you're getting a perfect solution, but maybe you're spotting something, and maybe that's the point. Oh, sir, he is ahead of the curve. on this 1 minus e to the minus x. Isn't this... Shh, no spoilers. We're getting to that. Okay. So on this graph, y equals 1 minus e to the minus x. Plug in x equals 0. E to the 0 is clearly just 1. 1 minus 1, 0. So we know y equals 0 at that point. We know as x tends to infinity, e to the minus x tends to 0, which means that y is going to tend to 1 minus 0, which is 1. So it's going to look something like this. And then the reason why I like these for science interviews, it's helpful sometimes if they have physical meaning. And as a commenter has said, isn't this graph just the capacitor charging equation? Yes. This is the graph. It's also for, it's for current. No, it's not for current for charging, but it is for Q and V for capacitors, which you may not have covered yet, and that would be totally fine. But what if you have no idea what a capacitor is? They would. This is what I mean. So it's more of an open-ended, does this have any significance to you? Because if you think about it, it was entirely possible to draw this graph without having the slightest clue what a capacitor is. And they are very aware that capacitors are a topic that come up around this time of year. So some students will have learned it, some haven't. So to expect it would to give some students a leg up, and that would just not be a meaningful place to have the interview. They're going to have the interview on skills that they know everyone knows, your forces, motion, and energy stuff, your electricity stuff, or the stuff that they know that no one knows, so that it's a level playing field. I would trust them to sort of, and again, even if you get a question which relies on something that some people know and some don't, it's not about what you go in knowing, it's about what you understand and where your absolute limit is and what your process is like when you hit that limit. Can you find new meaning? Can you push yourself forward? So don't worry about it. Trust them to guide you through it. But if you are someone who knows what a capacitor is, you could use that to guide you. You could say, looks like capacitor charging. But where this could go for someone, for all of you who, like I said, sort of bringing it to a spot where none of you know what's happening. What if I just adapt that ever so slightly and say it's y equals 1 minus e to the minus x times sine x, again for positive x. Well, I'm going to use the same idea that I had before about an amplitude envelope function, only this time, this function is going to be the amplitude envelope. So in fact, I'm just going to co-opt this entirely. When sine x equals 1, this will give where those maximum values are. And when sine x equals minus 1, it will be the negative of this graph. So it will tend to minus 1 there. And we know it's sine, so we know it's going to be doing some sine behavior in between, where it's going to eventually reach a steady state. This point around 0 looks like one of those special points, so maybe I'll just like look at that a little bit deeper. So again, what's the behavior? Could we maybe get a quick general symmetry of amplitude enveloping? Yes. Let's consider the function y equals some function of x times sine x. We know that sine x lies between minus 1 and 1, which means that if I multiply the whole thing by f of x, y is going to lie between minus f of x and f of x. In other words, if you draw y equals positive f of x and y equals negative f of x, whenever sine is equal to 1, it is going to touch the amplitude envelope on the top. And whenever sine is equal to minus 1, it is going to touch on the bottom. And that's the basic idea. But remember, this is not something you need to know. It's not in your syllabus. Amplitude enveloping is just useful for trig functions, right? That's when you're going to be seeing it most, yes. And it's most helpful because, yeah, I would say it's most helpful for sine and cos, which is why it's helpful for the scientists, because there's lots of waves that you can do with this, as we're going to see. And the engineers, actually. This is going to be good for you. So considering this behavior of this function then around, let me clear this. Whoop. My tech is not tech. Well, my tech is teching. I'm just not teching it well. Let me zoom out a little bit. Let's find out what's happening around the origin. So around the origin, we know, well, let's consider this two ways. And the reason why I'll do this two ways, by the way, is because it's helpful to, I'll get onto this later. Remind me to come back to that, if you can. So I'm going to first go with my old faithful of differentiating to find the behavior. It's first d second plus second d first. And when x equals 0, what is happening to dy dx? Well, this would become 1 minus 1, which is 0. And sine of 0 is 0. So I know actually, rather than the sine graph, which starts off with an upward slope, this is initially going to be, nope. It's going to be a little worse. It is going to start off flat, and it's kind of going to do this. So if I do that on clean axes, then we can see that it is going to and then it's reached its steady state. So this, for any sort of scientists out there, this is resonance. This is when you apply a driving force and you force something into steady state resonance. The amplitude slowly gets bigger until it reaches its steady state. And so that is the form that takes. So with any sort of science or application interview, maybe having a think about, does this function mean something? Do I recognize the look of that? And those sorts of connection formations are impressive to show. Okay, got a question. Do you have any tips for sketching functions inside trig functions? Yes, I have an entire graph sketching video all about that. So I would recommend you go watch that. But the main thing I would do with that is I would draw my component graphs. So if you want to see how I would do your suggestion of y equals sine of 1 over x, my top tip would be to separately sketch 1 over x and sine x, and then think about what happens when I put one into the other. So I can see, for instance, as x tends to infinity, 1 over x is tending to 0 slowly. And again, I'll be good and sketch my axes. 1 over x is tending to 0 slowly. And if I put, which means that sine will be tending to 0 slowly from above. Can I summarize L'Hopital's rule? Not very good at I'll give it a go. When considering limits as x goes to 0. I can summarize L'Hopital's. L'Hopital's is not in the A-level math syllabus, it's in the further math syllabus. If you have got that far and you can use it, then do. So I'll summarize that right afterwards. So here, I know as x is tending to infinity, y will be tending to infinity from above. I know that when x is tending to minus infinity, I can see from this component graph that the argument then going into the sine is tending to 0 from below. And I can see here that's going to be in this sort of part of the sine graph, which means it's going to tend towards 0 from below. I can see that as I move from positive infinity up to 0, this thing is getting bigger and bigger and bigger and faster, which means I'm going to start to move through the sine curve, but it's going to get faster and faster and faster until it's just like a in the middle. So it's not going to be very physically meaningful, but then this is going to do the same thing from the other side. But basically, I would look at the component graph and consider threading the needle. So as I start from x equals minus infinity here, what happens as I move towards x? Well, that's getting really big. Well, what does that mean when I start moving through the sine graph in the same way? Because it's that graph going into this graph, and so looking at them separately can help you thread the needle, is my best piece of advice for that. Common question, could you summarize L'Hopital's rule when considering limits as x goes to 0? So L'Hopital's rule, I'm going to be completely honest, is one I have not used in a while. But from memory, L'Hopital's rule is good for when you have a kind of 0 over 0 situation. So, quick thing with L'Hopital's, only use it if you know the conditions for it, because people trip up on that. Yes. Do I know them? Not off the top of my head. Not right now. Which is why I've been relying on more fundamental A-level syllabus material. But if you do, I'll start with what happens if I don't know L'Hopital's rule, because fear not. L'Hopital's rule would be good in, for instance, considering y equals sine x over x. So L'Hopital's rule, I'll let a mathmo tell you what. If any of you in the chat, so Invisible Toast, I'll let you help me out on this one. If you could drop a comment letting me know what those exact conditions are and whether I'm screwing this all up, that'd be great. Check me on that. The 0 over 0 condition, yes. So L'Hopital's rule is typically used for 0 over 0. So what happens here as x tends to 0? Well, that would be 0 over 0, which would blow up. Technical term. So what you can do instead is find the limit as x tends to 0 of the differential of, you differentiate the top and bottom. So differential of the top would be cos x, differential of the bottom would be 1, and you would consider the limit as x tends to 0 of this instead. And we know that the limit as x tends to 0 of cos x is 1. But in any sort of 0 over 0 situation, chances are one of those is due to a polynomial, just an x, but chances are the other thing is either due to sine or like an exponential decay. If you're going to infinity, but if you're tending towards 0, instead of using L'Hopital's, for an interview situation, it's very likely you're going to be able to use small angle approximation instead, which you might feel much more safe with. So for instance, here in small angle approximation, I know that y is going to approximate, sine x is going to approximately equal x for small x values. So it will approximate 1. If I were doing the same for y equals, for instance, 1 minus cos x over x, as x tends to 0, the top would again be equal to 0, but I could instead again do small angle approximation where I know that cos x will tend to 1 minus x squared over 2 for small x, which will be 1 minus 1 is obviously 0, so you'll just be left with x squared over 2 over x, which would just be x over 2. So it will tend to 0 as x tends to 0. So I would recommend, if you're not 100% confident on L'Hopital's, try and avoid it. You really don't need it. You shouldn't require it for what they're doing. And as I was kind of alluding to before, and it's something I'm going to get onto when I get into the physics phase kind of just about now. One good test you can do for yourself in these final days before an interview is think, not just, can I solve this problem? But how many ways can I solve this problem? Can I do it this way? Can I do it this way? Do I have another skill for it? I'm going to show that a lot in the physics question I've got coming up. But here, can I solve it with small angle approximation? Can I solve it with L'Hopital's rule? And I know, for instance, in math interviews, I remember someone got an interview question where they had to prove the volume of a sphere multiple ways. So before I go into that, Invisible Toast has said, L'Hopital's works when you have two functions divided where they both equal 0. So a 0 over 0 or plus or minus infinity, provided g dash of a exists. Here I'm considering the limit as the quotient approaches a. It cannot be used for 0 over infinity or vice versa. So infinity over infinity or 0 over 0 seems to be the rule for L'Hopital's for those who are confident using it. If we are asked to sketch something with sine x in it, which seems a bit impossible with the normal graph sketching methods, could I use a Maclaurin expansion? If you've got the skill for it, go for it. If they don't like it because they decide that Maclaurin is going to take you forever in a day and they only have 20 minutes for you to go through all of those differentials, they might coax you into another direction. Actually, that's a bit of fun. You suggested a good fun graph. Why don't I have an attempt at that and see how that goes? Just let's, because the whole point of this channel is for me not to tell you what to do, but to show you what to do. So you're suggesting y equals x plus sine x all over x minus sine x. Well, let's start with, as x tends to infinity, I know the x is going to drown out the sine x entirely. So y is going to approximate x over x, which is equal to 1. And as x tends to minus infinity, again, the x is going to dominate. So y will again tend to approximately x over x, which is equal to 1. So those are my asymptotes. When x equals 0, we get a classic 0 over 0 error. So instead, let's consider as x tends to 0, where again, we're going to use our small angle approximation to say that y is approximately equal to x plus x over x minus x, which is going to blow up. So I expect there to be horizontal asymptote of 1. It's going to blow up to 0. And I could also consider my component graphs. Do I want to go all the way into this? Hold on a minute. Could use a Maclaurin expansion. You could use a Maclaurin. I said someone got asked to derive the volume of a sphere in many ways. No, that was a maths interview, pure math, not engineering. But someone did ask for integration from first principles, so I might do a bit of that as well. Hadamok, where the clever trick was to evaluate the limit instead of Maclaurin series. That is one of the ugliest graphs I've ever seen in my life. You have all of the fun with that. Pure math modes, you go nuts. That is unphysical to me, and I am scared. Nope, not touching that one. For anyone wondering, the graph that has just been proposed in the comments is y squared equals x squared ln of 1 plus 1 over x squared. No. Peace be with you on that. Love and light. Namaste. Go your merry way on that. Not for me. So here, what would I do? So I kind of know what's happening at the extremes. Oh, this is fun. This is fun. I like this. Let me draw these component graphs. Because let me instead consider just on this one, y equals x plus sine x. So what's going to happen there is actually quite fascinating. Because if we have just the y equals x line, the sine x graph is just going to be oscillating kind of on top of that. And same thing with the minus x. It's just going to be oscillating on top of that. So it's kind of going to be doing, I mean, I shouldn't really have drawn these both on the same axes, but these got this cool double helix shape. So those are fun individually. Oops, wrong one. But like I said, I don't want to go too extreme today on the graph sketching front. And I worry that doing something like that would be unhelpful. But these are the sorts of skills I would use. Small angle approximation is your friend. Drawing your constituent graphs or your component graphs, that's going to be very helpful. Considering limits, all these sorts of things are just going to help you pin down values and make a bit more sense of this. So for instance, whenever sine x equals 0, it's going to be equal to 1. So every 0 point here. So every n pi, I know I'm going to get a value of 1. What I can also do here, for instance, I can rewrite this in a cheeky way, where I can call that x minus sine x plus 2 sine x all over x minus sine x, because then that just becomes 1 plus 2 sine x all over x minus sine x. So we can kind of see this dependence on the one line. And we can see as x is getting bigger, this guy is going to get smaller and smaller in amplitude. These are the sorts of things I would do. I think if this doesn't feel like a very natural sciences graph, so I'm just going to be a bit wary about that and say, this is not a standard you have to hit. And today we're just consolidating, we're calming down, we're getting everyone to where they need to be. Mathmos, go crazy. Go running with that one as well. Everyone else, I'm going to stop going on that one. Because I'm just, again, reminding you that all of these skills are available from the syllabus, and if you apply them competently and confidently, you will do well. A little bit on the differentiating from first principles. Or let me just check the comments just in case. Oh, and by the way, I don't have someone at 8 p.m. today, so I can carry on a little bit later. Because I really want to make sure I get to this physics stuff. Beyond symmetry about x and y axes. I was so lost. Still don't know how to do it. Okay, let me look at this graph. Another graph has been proposed. X squared minus 2 all squared and y squared minus 2 all squared equals 2. I don't like it. Do not enjoy. Well, we can obviously think about what the axes are. So when x equals 0, you get 4 plus, I just have, yeah, I'm going to leave this for the pure math mouse. I'm just getting the sense that I'm straying from the path of what today should be. So rather than get harder and harder and harder, let's make it easier and easier and easier. I'm going to let you guys chat that one out in the comments. Of course, squiggly shapes. Yeah, you'll probably get. Okay. What I'll do instead, let's consider a question actually from NSAA section 2 from back in the day. So it was considering, the idea was you had to kind of square like a triangular trough, which was kind of going backwards. That was filled with water, if you can imagine this. So it was filled, this was an isosceles triangle, and it was filled with water, and you needed to work out like the total pressure. I can't remember the exact form of the question, but it doesn't really matter because this is more about the principle of how to do integration from first principles if required. So if it's filled to a height, well, let's just say it's full. We know in general the extra pressure due to the water is rho g h. So at this point, x, the extra pressure would be rho gx. And then it was something like, as we get an element here, dx, going down, because this was an isosceles triangle, because this distance here was h minus x, then this distance here across was also h minus x. And so the area of that element, small area element, is h minus x dx. Might have been that. It might have been asking for the weight of the water or the force. It was some sort of situation like this. But the point was that a small force element is equal to pressure times area. So it was something like rho gx times this area element. And so to get the total force, you could like integrate between x is 0 and h of rho gx h minus x. And then perform the integral. So that is the idea behind setting up an integration for first principles. You consider an area element. So what is dA in terms of dx? And then kind of assemble the pieces. So for instance, proving the volume of a sphere, we could instead consider a small shell of thickness dr. The volume element of that shell would be the surface area of the shell times that small radial element. So if I integrate the volume, because the volume is 0 when the radius is 0, the volume, integrating the left-hand side, is equal to 4/3 pi r cubed. There you go. So it's just about setting up the element. That is if, again, more for the mathmos, if integration from first principles is something that can come up. For the engineers and the scientists, this is not basic syllabus. I would not expect this to be something that you get easily. This would be more guided through them teaching you from first principles, but I'm going to put it in for those for whom it will help. Go back to the comments for a little bit. Would they combine? Let me check. Is there anything else I need to talk about? An integral doesn't really test your ability. Integrals are more do with exposure. I would say these ones that I've shown would be a bit of ability, thinking about how to set up the elements to assemble. But you're right that in terms of actually doing integration is kind of a bit of exposure. That's a less well done, less sort of examined topic. But if it's a skill that you feel like you need, that is achievable for you, then go for that. I would not don't beat yourself up to try and get something you don't get. The point is to show them where your limit is and then show what happens when you push it. So it's not about what you know right now, which is why you should bring it back to things you're comfortable with. Don't push yourself to learn integration from first principles at this point. Don't push yourself to learn L'Hopital's at this point. Just push yourself to master what you know. Just providing it in case it's something you feel like you want. Could you get integration in NatSci interviews? You could get basic polynomial integration, certainly, because that's a year 12 topic. I would not, you won't be expected to do any like crazy ones. So you can absolutely be expected to do anything that was required for your ESAT spec. And if you did math 2, then integration was part of that. So it can come up there. For my college, I had to do a test like right before the interview, and they said there'd probably be integration. That does sound like Trinity, but I thought Trinity got rid of that test. I know they got rid of it for engineering. My engineers aren't having to do that. I know I had a guy get in for Trinity for NatSci a few years ago, and that test was difficult. But the point of that test was to sort of form the basis of the interview. So you did your test, and based on what you got right, they knew you were kind of fine with. Maybe then the stuff that you got wrong, they could then push on that. So again, really, you kind of can't lose with interview, because as long as you show up and do your best with what you've been taught, you're doing the right thing. It doesn't matter if someone's been trained to be up here and you've only been taught basic syllabus stuff in school. They actually don't have an advantage on you, because the point is not where you start. The point is how much you move. So the interviewers would be looking at them and thinking, all right, you're there, great, can I push you further? And the interviewers would be looking at you with your knowledge and thinking, great, can I push you further? And it's more about how much improvement you make in the interview rather than where you start. So again, that's kind of what I'm trying to get through today is don't stress about it. Just master what you know, and anything beyond what you know, it's their job to push you to get there. What if you are unfamiliar with calculus-based notation in physics? Like I don't understand the area element part. Ask them a question and they'll teach it to you. I very much don't expect this will come up. And if there's something that comes up where you could use it, they will have thought this through and there will be a way to do it without using that. So you should always have an ability to use skills that you do know to solve their problems. And if they require skills you haven't learned yet, they have to teach it to you because an interview is a lesson, not a test. Not a problem. And again, I would put a low probability on that coming up. Yes, these infinitesimal length questions can definitely come up for engineering. I have my Homerton engineering interviews on Tuesday, and I'm trying to study EEE, and panel B are both fluid mechanics specialists. I've had that question a lot as well. Should you go researching the specialties of your interviewers? And I think the answer to that is no. Because again, the interview is not about what you know coming into it. It's about what you understand. It's about how you process. It's about how you learn. It's their job to sort of take you from the syllabus and just sort of see what your foundations are, not what their interests are. It's about you and your potential. So yeah, I wouldn't worry too much about that. Just making sure anything that is in the syllabus is something that's mastered and you're ready to answer questions on. It was for Pembroke College. So apparently Pembroke is doing the pre-interview test. Did not know that. It's good to know. They said it will facilitate the interview itself. Yes, it will. Because it's just a bit of an extension of the interview where they test you across the board. They can see what you know to give you a really good opportunity to explain yourself in a topic you're confident in, to show your good process. And on the stuff you get wrong, they can then push you a little bit further, see how you learn, see how you develop on the spot. Okay, now we're going to pivot to physics. We're going to do a couple of questions. We're going to do vertical circular motion to start with. And I am going to remember to start sharing my screen this time. Can you imagine? Okay, so vertical circular motion. We're going to do tried and true classic from the textbook. We're going to roller coaster. So if it is dropped from a height of big H, a classic, and we have a loop of little h, a classic question might be, how high does big H need to be in order to ensure you can make it all the way around the loop without crashing? So what you need to know is that at the top here, well, let's consider the forces in all cases. We know from the syllabus that this is circular motion. In order for there to be circular motion, you have a resultant force acting towards the center of a circle. At the bottom here, the resultant force is the reaction force minus the weight. So R minus mg equals mv squared over r. And at the top here, reaction force acts down and weight acts down. And so I can say that R plus mg equals mv squared over r. Now I can also say that in the limiting case, the situation you have to avoid is where the reaction force becomes 0. So when that is true, mg equals m times v min squared over r. Those cancel. So v min squared equals gr. And I also know that the radius of that is h over 2. That is the minimum speed it needs at the top Then I can consider energies. Because I know that traveling from this point to this point, assuming no energy loss due to friction, is a simple conversion of GPE to kinetic energy. That gain in kinetic energy from 0, so the kinetic energy there is a half mv squared. And that kinetic energy must equal to mg times the change in height. So therefore, h is 5/4 of little h. Now, you may not have seen that direct route. That's okay, because there are multiple paths to doing this. I could instead have considered the kinetic energy at the bottom, and then separately considered when that gets converted, so the kinetic energy at the bottom is equal to mg big H. So the kinetic energy at the top is equal to mgh, and then you subtract off the GPE gain you have to put in to make it to the top of the loop. So that's a different way I could have got to mgh minus h. So it's kind of fun and creative coming up with all the different ways you can go about this. Right, satisfied with that? Time to check the comments. How do interviews exactly determine which student to select for the offer? That is a bit of a black box, but what I will say from my end is you can, let's add conversation. You can kind of just tell. There's a kind of, they're trying on brains, right? So they're kind of shopping for brains that are going to sit across from them at the supervision table or at the tutorial table for the next couple of years before you become the department's problem. So they want to make sure that you're a good person to want to teach for the next couple of years. So a good candidate, the sort of candidate who gets an offer, is the sort of candidate who can take a lesson that you're trying to teach them and get the absolute most out of that investment. And that will look like really engaging with their process, being really critical about their own understanding, challenging themselves, really playing with the ideas, taking it a little bit further, thinking, what does that mean? But also this fun sense of like an interview going well feels like the best game of ping pong you've ever played, where you are being pushed to your absolute limit and you're like, fighting for your life and like finding a standard you never knew you had, but your brain's on fire. And you're kind of just like bandying back and forth, and you're like, oh, I want that. Oh, bring me more of this. Yes, please. And that kind of like electricity is just something you can kind of just tell, right? And also bear in mind, like an interview is meant to test whether you are suitable for their teaching style. And you're teaching, you could be brilliant. You could be 4 stars. You could be getting phenomenal grades, and yet the teaching style just might not be good for you. It may be that you would not thrive there and you should not go there. So what they do is they test that learning style on you to see if it is actually good for your brain. Because some people prefer a much more structured, some people get their A stars because they sit there, the teacher teaches them, they're really good at receiving that and then replicating it, which isn't really the Cambridge way or the Oxford way. And so that's really what they're doing, is they're just sort of poking your brain to make sure it responds in a healthy way, because they want to know that if they bring you into the system, then your brain is going to function fine. They ethically don't want to bring you into something that isn't going to be good for you. So I would say it kind of like is that someone who thinks, oh, that could be this, that could be this. It's the kind of person who gets ahead of the teacher. I saw a question. There is a helium balloon in the back of a truck. Oh yeah, classic. Describe the situation as the truck suddenly breaks. Does circular motion come up a lot in engineering interviews? Yes, I would. That would be a really good one to test. So I think I've done it before as well. The ball falling off the sphere question, which is circular motion involving both forces and energy. Circular motion, obviously, rotation is a very important thing, especially in mech engineering. If you're thinking about engines, if you're thinking about lots of these things, rotation is an important concept. So it is something I think if I were an interview, I would want to check to make sure people were really confident on what exactly a centripetal force is. And I spoke about that a lot in my, I think it might have been my Out There video, where it's like, what is a centripetal force? What happens if those conditions aren't met? So maybe do a little bit of a deeper dive on that, where I really dig deep on that. From your experience, oh, I've mentioned that one. What topics would you say come up a lot for engineering? Forces, motion, energy, the end. Make sure you were with a little bit of rotation, so maybe a little bit of extra moments work, a little bit of circular motion. I don't think they would expect you to know things like full, because that is, some people will have studied that in an optional course in AQA physics A level. There's an engineering option instead of turning points that you can do. They won't expect you to go full torque, moments of inertia stuff, just the classic A-level syllabus. But basically, go through your A-level syllabus and think, what sounds vaguely engineering? Material science, extremely engineering. Stress, strain, springs, these sorts of things could definitely come up. So just have fun with it. Just think, if I were an interviewer, what would I ask? What feels important for engineers to know? What would you say is the most prominent questions asked in math interviews at Cambridge? So certainly your graph sketching. Again, math isn't really my specialty. Typically, when people engage tutors for math, they want people who did math, not people who did science and engineering stuff like I did. But I would say for math, if you think again about the syllabus, think about the things that people often get wrong. I would expect it to be mostly on the pure side and not the stats and mechanics side. I would expect it to involve a lot of graph sketching, involve calculus, involve sort of pure rigorous logic. Like, does that really follow? Like checking if you're making any assumptions, the deep math. Like, but why though? And also solving things lots of different ways. So for instance, completing the square to find the minimum point of a quadratic, or differentiating to find the minimum of a quadratic, or graph transformations to find the minimum point of a quadratic. These kinds of things. Like, can you do things multiple ways? Sad to see they're not interested in asking circuital analysis types of questions. They might be. I can never, by the way, I don't know everything. They can ask what they want to ask. Like engineering, especially if you're going for electrical engineering, circuits all the way. So just go for a no regret strategy. If you want to be as prepared as you can with anything that was ESAT material that is in the textbook. Have you done any challenging moment statics questions on these live streams? No, I haven't. But I'm about to do a good ball on a slope question. How can we prepare for the math side for engineering interviews apart from graph sketching? Of course. I would say things like optimization problems, maybe. Setting up equations, differentiating, setting to 0. Solving your polynomials, differentiation. Those feel like the main two. But of course, the best way to answer that is to go through your math syllabus and think, how could this come up in an interview? What could they be asking? Not sure how much my opinion is worth, but I would really look at questions that involve parity checks. I do like a good parity check. So that's certainly for math. So that's come up a lot in my TMUA prep for my guys going for like economics at LSC. So yeah, LSC requires, I think, the TMUA. So parity can be used sort of like evens and odds checks or positive negative checks. For instance, to find ranges where a composite function is positive or negative. We're getting a lot of comments about the tilting chessboards using dominoes and trominos and tetrominos and whatnot. Oh, tiling. That's a bit out there. Oh, interesting. Lots of people have been asked about tiling chessboards. Can you let me know what subject that was in? Parity checking. So, okay, parity check. And that's a good point. I want to know if you're using parity checking for strictly positive, negative, or also even odd. We've got some comments. Could magnetic fields be on a Fiznatsky interview? Careful. Magnetic fields was on the ESAT spec, so yes. I would say anything that was ESAT examinable, they're letting you know that's fair game. I would not expect to go into the full electromagnetism of the A-level syllabus because not everyone will have got there yet. So things from GCSE, things from ESAT spec only is what I would expect. And again, they're testing more the depth of your conceptual knowledge rather than the specificity of specific problems. Do you understand the forces that are at play in physics and how they fit together? So maybe at a high level, but not at a detailed level. What's the best way to handle questions on topics you've not covered that are on the syllabus? I'm a student from Ireland and have not covered differentiation. Let them know, because they might just go in and blindly expect everyone to have done that. It's perfectly reasonable for you to say, differentiation is not something I've been taught yet in class. So if that's required, I might need a bit of a sort of assistance on that. Could you show me an example of how one works? And maybe I can use that and apply it to this question. Because that is exactly what an interview is. Teach me something, let me learn how it works and apply it. That way, if anything, if you could successfully do that, that would be a really positive showing. They wouldn't think, oh, this person's so far behind. They'd think, damn, this person's on the front foot, asking for new information, asking to be taught something and using it well. First time, sight unseen in a high pressure situation. Grand. Chessboard question only for mathematics. So, Parity, you were talking about even versus odd. Questions like, can we tile a chessboard using 2x1 dominoes if we remove certain squares? That seems like outside my scope. There's a very specific type of brain that goes through pure math. I think you can tell in the way I go about it. I'm very science-based. But right. So chat over for a little bit. Let's do what I think is my final very important question when it comes to the physics. One that I've been using with all of my interviewees this week. And its premise is very simple. You have a slope. We have a particle on the slope. Particle has mass m. We consider g. Slope is on an angle of theta. I project it up the slope with the speed of u. And it has a coefficient of friction because this is a rough slope of mu. And all I ask my students, all I ask the candidates is, what happens? And here are all the things I think happen and how you can go about explaining it. So high level. I know it is going to go up the slope. It is going to decelerate. It's going to come to a stop. That is a thing that's going to happen. They can go, okay, great. One thing you might find is how far up the slope it travels. So we first, tried and true. We know it's traveling up the slope, so friction will oppose that motion and act down. And I want to just show you, there's a way to do this to just sort of gloss over the syllabus material. I really encourage you to dig as deeply as possible and really get to the heart of why these things are true. Don't just automatically say R equals mg cos theta. Why is R equal to mg cos theta? Always get to the deep why of even the most basic parts of the syllabus that you've been taking for granted. So here, fundamentally, I know F equals ma, where F is the resultant force. I know there is no acceleration perpendicular to that slope. And therefore, I know there is no resultant force perpendicular to the slope. Therefore, I know the force is balanced because the r minus mg cos theta is equal to 0 because it does not accelerate. So that is why r is equal to mg cos theta. Nothing is too basic for you to avoid explaining. They want to show, because those fundamental assumptions can often be the foundation on which they build really complex things. So to show an awareness of those assumptions and those deep understandings, so important. So then what we have is, as well, resolving forces, let's say up the slope. I know it's going to be minus mu r minus mg sine theta equals ma, where the masses will cancel, and I now have the acceleration is this down the slope. It is often very tempting now for people to do suvat, where s is what we're trying to find, u is u, v is 0 when it stops, and a is this monstrosity. So we know that v squared equals u squared plus 2as. So v is 0, u squared is u squared, minus 2 mu g. Look how I'm slowing down to avoid making any execution errors. I'm going to put the minus inside because I forgot my x. So I'm just going to write it as is inside a bracket with an x. So then moving that across to the other side and dividing through, x is equal to u squared over 2, because I should have multiplied it by 2, into 2g mu cos theta plus sine theta. Cool. That is how far up the slope it moves. Now, this is what I mean about trying to, how many different ways can I prove it? Is there another way you could have done this? And the answer is yes. We could have done this considering instead energy. Starting from the bottom, the kinetic energy is a half mu squared. And that kinetic energy is being converted into GPE and the work done against friction. So that is equal to the GPE gain, where if that is x and that is theta, the GPE gain is mg delta h, which is x sine theta. And that is also converted into work done due to friction, which will be mu r times x. So again, the m's will cancel. And u squared over 2 is equal to x into g sine theta plus mu g cos theta. So x is equal to u squared over 2g mu cos theta plus sine theta again. One using forces in suvat, one using energy. And then I say to all of my candidates, okay, so it gets to the top. What happens next? And it's a very common misconception to just say, oh, it's going to come back down. And I say, does it come back down? And they have to stop and think about it and say, hang on a minute. Once you get up here, the situation has changed. It is now attempting to go down the slope. So friction is now going to act up the slope. And what happens next depends entirely on the size of that maximum frictional force compared to the component of weight down the slope. Because now this is static friction, it's less than or equal to mu r. It does the bare minimum required to stop it moving. So if mg sine theta is less than or equal to mu r, then it does not move, then it stays put. And that happens, the mg's cancel. If I divide both sides by cos, that happens when mu is bigger than or equal to tan theta. And conversely, therefore, if the component of weight acting down the slope is bigger than the maximum available friction of mu r, then it will slide down again. And again, none of this is too extreme. This is all simple stuff from your syllabus, but applied with like general expressions and in a very rigorous, thought out way, not falling for any of the tiny conceptual traps. And then finally, I've been asking some of my candidates to calculate the speed. Let's say it does roll back down, calculate the speed it has when it hits the same point. And again, there are multiple ways of doing this. You could suvat it again, but I think the easiest way is to do it using energy. For me, the way I think about this is actually from starting here. So point A, the start point is where it gets launched, and then the end point is it goes up and comes back down again. Where in this case, because it's arriving at the same point, there is no change in GPE from when it starts there to when it ends there. The only energy change is that the kinetic energy it loses is equal to the work done due to friction on the way. Which is force times the distance of 2x. And so what we know is that x is equal to, so let's work out the speed. So let's make v squared the subject of this. Or I'll have to come back and find that expression. That's why I didn't delete it. But well, let's first cancel m's to make my life easy. Let's multiply by 2 to make my life easy. So v squared, and I equals u squared Nope. Execution error. Alert. A half mv squared is going to be less, so that should have been the other way around. I apologize for that. At that point, I just caught it. V squared should not be bigger than u squared. So in other words, if I rearrange to make v squared the subject by bringing it across, v squared is equal to u squared minus 4 mu g cos theta x, which is u squared over 2g into mu cos theta plus sine theta. This will cancel down to 2. So it's going to be u squared into 1 minus 2 mu cos theta over mu cos theta plus sine theta. And I can bring this all into one fraction. Mu cos theta plus sine theta minus 2 mu cos theta all over the stuff. This is more complicated than I thought it was, but as long as we apply brute force, the concept isn't tricky. Now it's just the math is tricky. So that cancels down. You just get sine theta minus mu cos theta all over sine theta plus mu cos theta. Now, the reason why this gets interesting, folks, is because if we divide top and bottom by cos theta, we get tan theta minus mu all over tan theta plus mu. And if you remember, in order for v to be real, v squared has to be positive, which means that mu again has to be bigger. No, which means that mu has to be less than or equal to tan theta in order that this thing on the top is positive. So it's funny, this thing has shown up again in a different part. And the reason why I like this is it really shows what they're going for, which is it's just ball on a slope, energy, work done, friction, simple concepts. But when you dig deep enough, these patterns, these things seem to come up again and again and again. And that's what they're trying to train you to see. So I'm going to pause there for a bit and take some questions. Right. Oh, someone said, thank you. Your videos have been a great help. I feel much better about the interview. Here to help. Stay tuned for here. I'll just do a little bit of a wrap up after this on the sort of final mentality and things to do at the very last minute. I think conceptually I'm done with what I want to cover, and I just want to spend some time going through mindset. So hopefully that also helps you a bit more. Would they appreciate the fine details if we're explaining it? It depends on what you mean by fine detail. If you playing buzzword bingo, then no. If it's you showing what something means and what your understanding of it is, then absolutely. They love a good assuming no energy loss due to friction, because it shows that you are paying attention to why that is an important consideration. So I would say show everything you've got. Leave nothing left on the table. Such as there is no acceleration perpendicular. Oh, yes. Oh, absolutely. Those, because I wouldn't even describe that as a fine detail. I would describe that as a fundamental detail. And those are two different things. A fine detail is like the name of something. A fundamental detail is the kind of stuff that's so easy that you typically overlook it, but that's exactly the stuff to bring out. So for me, I would absolutely be saying there is no acceleration perpendicular to the slope. Therefore, there is no because there's no acceleration, there's no resultant force, so therefore the force is balanced. Showing, if you can start with like a quote, like from, so if you say, okay, according to Newton's first law, this thing will continue moving in a straight line unless acted on by a force. Or according to Newton's second, we know this. If you can start from like the fundamentals and then work out, ooh, that's yes. Sir, for what are you teaching this? This is a student of IIT. This is a very easy question for me. So this would be for this question here, the ball on the slope question. This is for NatSci and for engineering, and it may be easy to you, but can you explain why? So if you can give a very, very competent explanation showing all those points again, then they would say, okay, that's his level. Let's find a harder question. And they would always try and poke you at your absolute level. Could you also perhaps do it the long way? So yes, you could do it the long way. So you could absolutely do it the long way. I only did I did it from the start point to the same start point. You could also have done that last part from the top going to the bottom. Absolutely. You could also have done suvat, starting from u equals 0, going to v equals v. You can work out the new acceleration, and the distance is the x from before. So all of those are available to you. You can try them out, see which one fits. But the point is the competence to prove the same thing multiple different ways and find these inherent truths lying underneath it and where they show up again and again. That's kind of the beauty of the physics that you're kind of there to solve. Also, somebody I know was asked to interpret a graph after sketching it. I sketched. I'm pretty sure I sketched that graph last time. If I didn't sketch that graph last time, I should sketch that graph this time because it's fundamentally important. I'll just very quickly go into this. So the just in case it isn't there, the a over r to the 12 minus b over r to the 6. So as r tends to infinity, these both tend to 0, so y is going to tend to 0. As r tends to 0, well, what you can do, in fact, let's not even consider a and b. I'm just going to make them 1, just for ease. If I multiply top and bottom by r to the 6 here, this becomes 1 minus r to the 6 all over r to the 12. And we can see that as r tends to 0 on this one, this goes to 0, so it becomes just 1 over r to the 12, which will tend to infinity. So y will tend to positive infinity. We can also differentiate to take a turning point. So that was r to the minus 12. So minus 12, r to the minus 13, plus 6, r to the minus 7. So it's minus 12 over r to the 13, plus 6 over r to the 7. Where is that equal to 0? Well, let's multiply by r to the 13, and you get minus 12 plus 6 r to the 6 equals 0. 6 r to the 6 is 12. R to the 6 is 2. R equals the 6th root of 2. I can also say, where is y equal to 0? That's when 1 over r to the 12 equals 1 over r to the 6. So when r is equal to 1. So putting this all together, it does something like going to infinity, doing like that. So that's 1. That's the 6th root of 2. And if you run that through, you'll get a y-coordinate of 1/4 for this particular situation. Now, the reason why this graph matters so much is this is the graph of potential of 2 atoms in a chemical bond. It's the Lennard-Jones potential. And so they will sit here in this equilibrium position. If you try and push them together too much, you will get electrostatic repulsion of the electrons. And then if you pull them apart, you kind of lose that. But you have to put energy into breaking the bond. This also does resemble the strong nuclear force. So it is a very important graph. And I think I did it last time, but it was so worth recapping just in case I hadn't. Things such as the diffraction envelope you discussed are things I think one could reasonably get, but the other graph I mentioned, how is one expected to be able to interpret something like that? You interpret it by thinking, does this look like something I've seen in physics or chemistry? So this looks like the potential energy of 2 atoms in a bond, or it looks like the strong nuclear force. So kind of tie it in if you've seen a similar graph in your textbook. Should I expect questions on waves for an engineering interview? You could absolutely get waves in an engineering interview. Anything in physics is fair game. For instance, it is important to consider waves, and particularly the standing waves in resonance, if you're thinking about the classic Tacoma-Narrows Bridge disaster. So waves, resonance, standing waves, all sorts of things that can come up. Waves are also good because they have periodicity, which again makes you think of rotation. So there's a lot of overlap there. Waves, good topic. What is an example of buzzword bingo? Buzzword bingo is when someone says a bunch of words thinking that the words themselves do the heavy lifting for them without them having to actually explain what they mean. So if you're sitting there waxing lyrical about Bose-Einstein condensates and scandium precipitates and airplane wings and blah, 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 like these sorts of things, I don't mean to diminish you if that is so your jam. But the point is, saying the word enough is not enough for them to think you're intelligent. They would rather you show that you understand what this means rather than just throw a bunch of words out and hoping it sounds intelligent. So that's kind of what I mean by buzzword bingo. You can kind of, just hopefully that's given a bit of a sense. Sir, please can you make a video on the solution of a physics question, which was a tough question? You can find that question by searching toughest physics question of events on YouTube. I'm not going to do that right now because this is the final preparation we're doing before Oxbridge interview. The time for really complex problem solving was early on. I think right now, in terms of strategy, what we want to do is to consolidate and make sure your skills are as strong as possible for the thing. Just syllabus material will do for now. Now, final things I want to say. You get into your interview. How are you going to handle it? What do you do? I think that you just remember that you're ready for anything, that this is a lesson, not a test, and that you are ready to have the best lesson of your life. It is genuinely so much fun when you're bandying back and forth with the interviewer about a subject matter that you're really passionate about. If you go in thinking it's a test and that you're going to be really deeply scrutinized, you can kind of get in your own head and not show your best work. And I want to tell a really important story, which is well, actually, I'll start by saying what they're looking for. Remember why you're there. You're there because you love your subject and you want to get a really deep understanding of that subject. And you show them that love by taking really good care of all the important detail, getting to depth, saying why something's happening, showing that you understand the forces that are connecting these ideas. Because that shows you have the motivation to dig deeper and do the work that's required to build the systems that they're going to try and teach you. It should feel like a phenomenal game of ping pong, bringing you to like the absolute best of your level. They want to see that process by which you go, okay, well, this and this and this and this, and I can hold myself together in the face of an unseen problem and stay upright and get my way through it. And I'll tell in a story, which is back in my day when interviews were still in person pre-COVID. There would be a waiting room where you would wait before each interview. And a lot of times if existing students had time, they would pop in and kind of just chat. So when I was in my first year, I sat in the waiting room chatting to people about to take interviews. And I will always remember this one guy because he was just a nervous wreck and he was super tense and like, oh, it hadn't gone very well. And I was like, okay, this is not helpful to him. So I said, okay, I want you to tell me about something that you are so interested in that has nothing to do with science. He was like, what? I was like, trust me. And then he's like, okay, well, I really like English. And I was like, oh, didn't expect that. Tell me more about this. And he was like, yeah, I really like this author and this author. And he was like, oh, because it goes like this. And then he did, and I went, that. They want to see that. They want to see that moment where your eyes light up, where you're like, yes. Like, I'm so interested in, like, that internal driving force is what is required to overcome that external pressure of the situation. And so doing something that brings that love, that excitement out of you, regardless of what it is, especially if it has nothing to do with your subject, that's what I advise you do in the minutes before going into an interview. Not beat yourself up about like, do you remember this? What's this formula? What's that? I advise wipe the slate clean and just think about something that like gets you excited personally that isn't to do with the work, because that makes your eyes light up. That gets you ready to go. That gets you like interested to learn and engage with them. And when he came out of the second interview, he said, I really wish I'd spoken to you first, because he said that the second interview went so much better. And so that, I think, is a really good piece of advice to get you in the right emotional framework, to get you started on the right foot, and to go in and look excited to be there. Because again, this could very well be the only tutorial / supervision you get, but you've made it. You for at least one day, you get to be an actual Cambridge or Oxford student and get this level of one-on-one, like elite level, like gameplay with your brain, pushing you to be at your absolute best. It is such a privilege. And for you to be able to go in bright-eyed and really enjoy and make the most of the experience will make it much better for you, but also will turn off that sort of amygdala reptilian brain thing that would shut your brain down and lets you kind of think, oh, yeah, I am able to think about this. And it lets you put your best foot forward and come up with solutions that you might not do if you were really, really nervous. So that's the last thing I really wanted to talk about. Now I'll take a few final questions before we wrap. Also, for the any questions for us part of the interview, does it matter what we prepare if we bring something? Not really, although I will say, because they always have a few canned responses, because it's good to have a few canned responses. They're used to it. I think a great question is if you have a follow-up question about something they've taught you. So like I remember asking a follow-up question in mine. But I was doing it more as we were going. I in my second interview, it was on graph sketching to do with the Arrhenius equation, rates of reaction stuff. And the gradient is the negative activation energy, and so you can get the activation energy from the gradient of this graph. And I just kind of thought, like, wait, can the gradient ever be positive? But if the gradient was positive, that would mean you have a negative activation energy. Can you actually get a negative activation energy? He went, oh yes, and he explained it, and I was like, what? So that maybe something like that to show that you've like really grappled with it. And if you have follow-up questions about like the topics, feel free to ask them sensibly. Like you can't keep them there asking question after question, but maybe just sort of like, because again, this is a lesson, not a test. This is your chance to like ask your Oxford at Cambridge level questions. If something comes up that you're curious about, ask the question. Will I be given paper in in-person interview? Yes. The end. The day before, should you focus on work or improve your mental state? I would not. What you don't want to do is to find like a black hole. You don't want to look at something and think, "Oh my god, I don't know this," and then panic yourself. So day before is all about reminding yourself what you do know. I do know this about science. I do know this about chemistry. I do know this about math. I do have these skills. I don't really care what they ask me. I know I have this, because when you retreat to like just your core skills, those are the ones that are going to be there for you, and you want to feel like those are good enough. So beyond that, also get a good night's sleep. And top piece of advice: if you are traveling to stay overnight before your interview, piece of advice I picked up from the British cycling team for London 2012: bring your pillow, because your body will be used to it, and you're more likely to get the good quality night's sleep that you need right before an interview. Might be a difficult question to answer, but would they prefer a candidate who isn't too enthusiastic, dashes through the problems as if nothing is really too difficult, and not speaking his thoughts? They want you to speak your thoughts. That is the fundamental thing, because they want to know that you're not accidentally getting this right. They want to know that if you are working on a problem sheet on your own, you will be fine. Now, with that said, does everyone have my personality? No. There are a lot of people who are very good at science who are very introverted and aren't big personalities, who are like screaming about how much they love science. That's fine. But as long as you can say, like, do the work and say, well, this is this, is this, is this, they can't have a problem with it. The one thing I would say, though, is that silence in an interview is death. So that's the only thing I would say, is to push yourself, because let me put it this way. If you are currently writing something on paper, it's because you are thinking something. If you are thinking something, that should be done out loud so that they know. Full stream of consciousness, just so they can see what's happening. They won't intervene unless they absolutely need to, but that's the gold dust. Or someone who's very passionate, enthusiastic, but needs some help with the questions. Passion versus ability. Ability, because it's not summer camp. Like it would be unethical to bring someone in who's very, very passionate, but whose system wouldn't be appropriate for what they would do to you. Because remember, you've got lectures 9 a.m. till 1 p.m., 6 days a week, multiple labs, multiple supervisions, on top of everything else you're trying to do with your life. It's not suitable for everyone. And so they want to make sure you've got a good level grappling of the understanding, so that it would be ethical to bring you in. So I would say that competence with the science would matter more than the enthusiasm, but enthusiasm does show the emotional driving force to put the work in to get there. So I would say lack of big personality is not to your detriment. Lack of skill is. Do you think it's worth reading ahead for year 13 component preparation? No. Given this advice by a chemistry teacher at school, but wanted to hear your thoughts? No. Because I don't think they can reasonably expect you to know something you haven't been taught. I think that teacher is acting under the assumption that an interview is what you know, and an interview is not about what you know, it's about what you understand and what you can learn. It is, if something comes up and you haven't been taught it, it's perfectly okay to say, this has not come up yet in the syllabus. What are the sort of, I feel like there's some sort of foundational knowledge I haven't been given yet. Can you sort of, maybe if you lay out the fundamentals, I'll be able to apply that. It's all about application of understanding, whether you bring it into the room or you're given it in the room. So I wouldn't worry too much about calculating like all the different equilibrium constants and things, and like the phenol, like aromatic chemistry, for instance. Like, I wouldn't go into the deep cut year 13 stuff, just in case. If there's something you think, like, I really want to get really good at mole calculations and you want to test yourself a little bit further just to test your core understanding, you can consider it, but do not put that much pressure on yourself to finish the entire A level of the next week. You're a gap year student and finished further math and chemistry A level. Will they ask me year 13 content? Maybe. I think unlikely, because they're more likely to give everyone the same interview to make it a fair test. That said, the point of an interview is to find out your limit and push. So if a question, for instance, we saw that graph sketch which related to capacitors. You will know capacitors, and so you will be able to bring it up. And maybe by opening the door, they then try and push you on that to find your limit and push you. So in relative terms, everyone is just being pushed past their limit and seeing how they respond. So for you, that might involve year 13 content because you've done it. But I don't think a question will be based entirely on year 13 content, because then they couldn't use it with everyone else. It's hard not to compare yourself to. Yeah. You don't compare yourself to everyone else. Just think like, did I learn something? And that's what I say to all my students. As soon as they come out of the interview, I chat to them, I say, what did you learn? Because if you learned something, then the interview went well. If you found it difficult, it means the interviewer trusted you enough to push you like that. So a lot of the times, people who think they've done the worst end up doing the best. What do you do if they ask you a question and you genuinely have no idea at all? That happened to me. Go watch my video on that for my actual thing. They will jump in and they will give you a hint if you are completely missing the point, like I was. In general, what you should be trying to do is not answer the question, but to answer something related from the syllabus. So in my last video last week, I did something similar where I was trying to explain how rainbows work. And I went, I don't know how rainbows work, but I know how dispersion works. And so I started talking about dispersion. You put white light into a prism, and then the refractive index is different for different colored lights, and so it splits. And so I went, maybe it's that. And then I also went, okay, but that wouldn't necessarily explain it. So maybe it's diffraction. So I explained single slit diffraction pattern and how that changes with wavelength. So I didn't answer the question. I used the question as an opportunity to demonstrate what I understood from the syllabus. So I answered the question I wish they'd asked. So when I can't do that, retreat. Where do I retreat to? Syllabus. Say what I know from syllabus. See if I can walk my way forward back to the question. Queen's College. Hold on. Pause. I need a drink. Queen's College do not use the whiteboard for engineering interviews and expect me to show my written work to camera. I feel like I should narrate everything I write because there will be pauses in between. Yes. Everyone should narrate everything all the time, full stop, the end, always. Because that's the stuff. That is the stuff they want. So look at how I'm commentating, right? You can see everything I'm writing. I'm commentating anyway. And so because you're not necessarily writing down everything you think. So you can be thinking around what you write. And so it's just giving you the full sort of director's cut of like exactly how you work, exactly how your brain fires. So talking out loud always. Also, make sure you're not talking like just out loud at the paper. Make sure it's a conversation with them. They want it to be a back and forth conversation. Because sometimes people kind of just go, well, this happens, and then this, and then that, and then this, that. Make it a conversation. Well, that's this. Like, actually explain to them what you're doing. Oh, this is my advice. Someone says, my interview is in real life. How easy do you think it is to find where you're going? Give yourself plenty of time. Aim to arrive 5 to 10 minutes early to give yourself getting lost time. Realistically, they know everyone's in the same boat, so things should be well signposted. You can map your route beforehand. There's usually plenty of time between interviews, so you can kind of find the place and think, all right, when the time is right, I'm going to go up there. It's going to be fine, and get there early, because the last thing you want is to be arriving there late, start stressed, start on the back foot. Don't show your best work. Show up early. Thank you, Mr. Flynn. This has been really helpful. Good luck to everyone else too. What do you think the hardest interview is between NatSci engineering and pure math? I would say pure math, because that's what I'm worst at. But it's everyone to each their own, right? Like, it's going to be, it doesn't really matter about comparing the different ones. It's about you going in and having like the most fun with the coolest, best lesson you've ever had in literal Oxbridge. Focus on what's in front of you, not what's around you. Could interviews try and catch you out by asking trick questions? I wouldn't say catch you out, but they could easily ask questions that are often misunderstood. Things with conceptual things that people get wrong a lot. So for instance, in my derivations video, there was the question about the ramp, where a lot of people forget that displacement downwards is negative. So there might be traps like that, but it's not like a specific gotcha question. It's just making sure you're holding yourself to the highest possible standard and not making those mistakes, as it were. How can you tell after an interview if it has gone good or bad? You can't. You have no idea. You are too busy focused on exactly what you're doing and how you're feeling in the real thing. You can't see the forest for the trees. You just can't. A lot of the times when people think it's gone badly, it's actually gone well, because they've been pushed past their limits, but they've taken the hints and eventually limped their way across the finish line. And because they've limped their way across the finish line, they think it's gone badly. That could work. So you do not, the second you get out of the interview, it never happened. Wipe it clean. And just like, nope, never happened. I am just going to put in my earphones. I'm going to talk about anything else. Call up your best friend, have a gossip, just put it behind you. Put it behind you. And yeah, move on and just find out if you got it. So, any wisdom about Komsky interviews? Don't do them. I'm joking. Komsky interviews, I would say go through your MAT tests. Those question 5 and 6 questions about like logic and process and algorithm are quite fun. Good thing to do there. Do you think being overly enthusiastic, sociable is a bad thing? It's a bad thing if it doesn't vibe with their style. So socially, you want to meet them where they are, because it's a little bit of nervous energy is totally understandable. And hi, look who you're talking to. But I think when you get there, kind of just like match their energy, right? They're going to calmly guide you through the interview. You should calmly meet them. You should show like excitement behind the eyes, but you shouldn't be like screaming at them, for instance. So just match their energy as best you can, and then let the science be the science. Do you think the interviewers could ask particular questions based on their own interests? No. They should be asking things based on the syllabus. For instance, my math interviewer has a PhD in applied maths and theoretical physics. Higher chance I get stats? Not necessarily. They know what the first year content is. Chances are their interview is based not on their interests, but on the first year syllabus, just making sure you're close enough to be able to hit the ground running with that. It's more likely to be based on what you will be doing in first year, not what they did in their PhD. That said, stats could obviously still come up. So be prepared. You don't want to you don't want the regret of thinking I should have prepped that and I didn't. So make sure you're safe from that. Great. I think that is everything. Good places to find questions for engineering physics. Yes, there was a good one. If you watch my last video, someone recommended one at the end of that. One of my students looked at that. He said it was very good. So check that. I don't have it off the top of my head. Will they ask about like experimental techniques in the sciences? Absolutely on the cards. Will you still upload videos after interviews are done? Great question. Yes, I am still planning on doing that. I do not think I can do it next week because I'm just absolutely loaded up with actual interviews that I'm doing, interview prep. I think after that, I'm going to do a couple of the evening live slots doing a TMUA and ESAT for the January cycle. I've got a few students doing those on top of my live solves. And then after that, I'm planning on carrying on my tutor seminar series, going through things I think are not particularly well taught and like how I conceptualize them that make it make sense for me. Things like your CVAT connected particles, maybe some things for like the IB physics. I know a lot of people struggle with greenhouse effect because it's not taught well. So I'll probably go and do deep dives on individual topics as we move through to exam season. Brilliant. All right, guys. I'm going to have to leave it there. In fact, it's probably 6 minutes over where I should have left it. But hopefully this shows you all you need to do. Just calm it down. Just show them what you know from the syllabus. Use what you know to answer the questions. Have fun. Go in there bright-eyed. Have the absolute best time having the best lesson of your life. And just find out what you're made of. So, with that said, go in there. Do your absolute best. I had something. What was that? I had something earlier. Ah, that was it. Give them hell. All right. All the best, guys. Good luck. And feel free to post and let me know how the interviews go, how that went, and I'll catch you on the other side. Good luck, guys. Take care.